Hi everyone, welcome to section 9.2 where we look at function notation and take another closer look at domain and range. So function notation to start is a symbolic notation that's used to write a function in different ways. So with this type of notation, what you're going to notice is that f of x is going to be a replacement for y. So we'll often use a lowercase f, and we'll say f of x is another way to describe y. But the reason why we want to use f of x as notation is so that we can do certain types of substitutions. So we're going to jump straight into the first example and show you how function notation works. So if we give you a first or initial function for question 1 that says y is equal to 3x minus 4, we're going to find each of the following using function notation. Now, as we mentioned already, f of x is a replacement for y. So if I say f of x instead of y, we can say that f of x is equal to 3x minus 4. What I'd like for you to recognize is that anything that comes inside those brackets is going to be what we replace x with. So in this case, because it's f of x, the variable in place is just an x. But when we start to give you different types of function notation, so let's say f at 3, what that means is we want you to remove remove x and replace it with 3. Now, anytime you do a substitution, please be mindful that you need to do those substitutions inside brackets, especially if we have negative signs involved. We don't want to make operation mistakes. So instead of 3x, we're going to have 3 and replace that x with the 3 from the bracket. And then we've got minus 4 to finish off the function. So now it just becomes an exercise in simplification. So 3 times 3 would be 9. And 9 minus 4, of course, is 5. So f at 3 is 5. The very cool thing about function notation is if you were to graph the original function, y equals 3x minus 4, when x is 3, your y value is going to be 5. So you'd have the ordered pair of 3, 5 on that graph. So if you have your calculator handy and you want to try that, give it a go. But we're going to use this function to analyze a few more questions with this function notation. So part B says find f at 0. So what we're going to do is go back to the original function f of x, or y equals if you'd rather. Every time we see an x, we remove that x and we replace it with what's in the brackets. So in this case, it's 3 times 0 minus 4. So f at 0 is going to be 0 minus 4, or negative 4. Now in part C, we see the importance of brackets. We want you to find in part C f at negative 10. So if I have just 3 and then I don't put negative 10 in brackets, it looks like we're supposed to subtract 10, but we know it's 3 times x, so it should be 3 times negative 10. Again, just be mindful to put those substitutions inside brackets. So 3 times negative 10 minus 4 gives us the value for f at negative 10. So negative 30 minus 4 more is going to be negative 34. In part D, we've got f at 0.2. So once again, instead of 3x, it's 3 times 0.2 minus 4. So if we simplify this a little bit further, f at 0.2, 3 times 0.2 is going to be 0.6. And when you subtract 4, we get an overall value here of negative 3.4. Next, we have something that looks a little bit strange. We want you to find f at w. Again, every time you see an x, pull the x out and replace it with whatever's inside the bracket. In this case, it's just a w. So we'll have 3 times w instead of 3x minus 4. Now, there's nothing we can simplify here because there are no like terms to combine. Last question in this case is going to be, again, the most challenging. So if we have f at a plus b, what we want to be mindful of is that wherever that x was, so instead of 3 times x, we're going to replace that x with everything inside those brackets. So we're going to have an a plus b in brackets. So there's our 3x minus 4. Now this is going to require us to open up these brackets a little bit so we can distribute through And we can say f at a plus b is going to be 3 times a, or 3a. 3 times b is positive 3b, and then we've got minus 4. Once again, we don't have any like terms to collect, and this is as far as we can go. The next few examples are giving us new functions to start. So with example number 2, it's giving us function f of x, which is 3x squared minus 2x plus 1, so that's a quadratic function. And it's also giving us g of x, and it's defined differently. It's 2x plus 3. What you'll notice is we're using different letters for function notation. One of them is function f, and the other is function g, so that we can keep them straight. What we want to do is basically combine these functions in different ways. So in part A, it says find g of x minus f of x. So what that means is you're going to start with function g, which we know is 2x plus 3. If you want to keep that in brackets, sometimes that helps with the operators. Then we're going to subtract, so there's my minus, and we need to put f of x inside brackets. So all of function f is 3x squared minus 2 times x plus 1. So this is what we have in terms of g minus f, essentially. So if we clean this up and simplify it, we just want to remove our brackets. 2x plus 3 stays as 2x plus 3, but now we need to distribute the negative sign through that last set of brackets. So you'll have a negative 3x squared. Negative times negative 2x is positive 2x, and negative 1 times positive 1 is negative 1. If we put this in descending order of power, we've got negative 3x squared first, 2x, and then 2 more x's is going to be a total of 4x. And then for constants, we have 3 minus 1, or positive 2, as your final answer. So this is what we have for g of x minus f of x. Now, 2b looks a little bit different in terms of the notation. You have a 2 in front, and then you have f at negative 2 behind it. What this essentially means is you're going to multiply 2 by whatever the value of f at negative 2 is. So what I like to do is actually make a substitution all at once. So I've got 2 out front, and then in these square brackets, I'm going to offset it with f at negative 2. So what that means is instead of 3x squared minus 2x plus 1, I'm going to have that 3 up front, but we take out the x and replace it with negative 2. So you'll have 3 times negative 2 all squared minus 2 times negative 2 plus 1. Again, that's inside square brackets, so we want to make sure that we evaluate inside first because we know BEDMAS rules. So leave that 2 on the outside, and on the inside we'll have 3 times negative 2 times negative 2, of course, is positive 4. Negative 2 times negative 2 again is positive 4, and then we're adding 1 here. So if we clean up those brackets a little bit more, 3 times 4 is 12, plus 4 plus 1. And then we can work inside those brackets. 12 and 4 is 16. If we add 1, we've got 17. And 2 times 17, of course, is 34. So in this case, we didn't just have to deal with function notation, but we multiplied the whole thing by 2 after the fact. Now the last example in this set, part C, looks very different. We've got 3 times f at 0 plus 4 times g at 1. Now, sometimes I have students who evaluate these kinds of expressions in parts. So they'll calculate f at 0, then multiply by 3. They'll calculate g at 1 and then multiply that by 4. But I find it sometimes a little bit awkward to pull all those things back together and not make any sign errors or miss certain parts. So I'm going to write this all in at once. We've got 3 times, in brackets, f at 0. So we're going to look at function f and replace all the x's with 0. So we'll have 3 times 0 squared minus 2 times 0 plus 1. So there's my, essentially, that's f at 0 inside those square brackets. But if we keep looking at the expression, we're adding now 4 times whatever we get for g at 1. So we're using function g as our reference now. So instead of 2x, it'll be 2 times 1. So we're replacing that with 1. And then we still have plus 3 in that function g. Whoopsie. Let's Let's fix that here. Plus 3. And then we can finish that square bracket. So now let's continue working this from the inside out. You'll have 3 on the outside. 3 times 0 is still 0. 2 times 0 is 0. And then we have plus 1. So we've got 0 minus 0 plus 1 in those brackets. In the next set of brackets, we have 4 times. 2 times 1 is 2 plus 3. So we can keep cleaning this up. We'll have 3 times 1 essentially, plus 4 times 5. So we've got 3 plus 20, or 23, as your final answer. The next set of examples are slightly different. We're asking you to sketch a graph, and when you sketch a graph, you're building your own table of values and seeing how those points connect. So when we talk about a table of values for our first function, what I want you to be very careful of is choosing appropriate values and making sure you have enough points to get a good feel for how the graph is behaving. If we have the equation y equals 3x plus 4, what we know is that this is going to be a straight line graph. In order to graph any straight line in the whole wide world, all you need are 3 points. 2 points will always make a straight line, but a third point is going to be used as a bit of a check. So what I want to do is make a table of values. So we've got an x value, and then we have our y value, and we can choose whatever we want for x and solve for y. So we're choosing our input and we're discovering the output. So I always suggest you find things like intercepts. So we could find the x and the y intercepts, and I'm just going to do that scrap work over in the margin. So for an x-intercept, what we know about every x-intercept in the whole wide world is that we can let y equal 0. So if we take that equation and we say 0 is equal to 3x plus 4, then we can subtract 4 from both sides. So negative 4 is equivalent to 3 times x. And then we divide both sides by 3. So you get negative 4/3 as your x-intercept. So what we know is that when x is negative 4/3, our y value is 0. Now for a y-intercept, we can do that or find that by letting x equal 0. So if we have y equals 3 times 0 plus 4, then y is going to equal 0 plus 4, or 4. So when x is 0, our y value is positive 4. So we found both of our intercepts. Those are 2 points on the grid that we know for sure. I'm going to pick a third point as a check and maybe even a fourth point. So what you notice on my table of values is I have something in the negatives, and I have 0, but I don't have anything in the positives. So what I'm going to do is balance this out a little bit. I'm going to choose positive 2 for my x value. So if we let x equal positive 2, then y, again, this is just scrap work. Y is going to be 3 times 2 plus 4. 6 and 4 gives us a value of 10. So when x is 2, our y value is 10. And I might pick negative 2 just to round things out as well. So if y is negative 2, then we'll have y equals 3 times negative 2 plus 4. So y will equal, in this case, negative 6 plus 4, or negative 2. When x is negative 2, y is negative 2. Now we have sufficient points in order to graph this function. So when we draw this grid, if you find points that are too extreme, you don't necessarily have to label them. But I'm going as high as positive 10 here, and as low as negative 10. Again, you want to make sure you label your axes, x's and y's. And for my horizontal scale, I'm only going as far as negative 2 to the left or positive 2 to the right. So I'm going to spread this scale out a little bit. There we go. So let's plot the points. We've got negative 2, negative 2. So when x is negative 2, my y value is negative 2. So we've got a point here. I'm just going to change colors of my pen here. So we've got 1 point. We've got -4/3 for an x value and a y value of 0. So -4/3 is just -1 1/3. So we want to make sure we put that in the right spot. Then we've got 0, 4. And then our last point is 2, 10. So now that we've plotted all 4 points, we can connect the dots. So when we connect the dots for this function, we can make a nice smooth line. Some of my points are off just a smidge. Just line this up properly here. There we go. It helps for you to be using a ruler when you do points like this, but we can see this is your linear function y equals 3x plus 4. What we also want you to do is state clearly what the domain and range of the function are. So the domain, if you recall, are all of the x values, and you have to think about that as how far left the graph reaches to how far right. So the domain starts at -infinity, so this is interval notation, and it reaches to the far right, so we reach all the way to +infinity for an x value. When you think about your x-axis, -infinity is far left, +infinity is far right, so your domain reaches left and right. Range is bottom to top, so we're wondering how low this graph starts to how high this graph goes. So in terms of lows, -infinity is the bottom of your grid for y's, +infinity is the top of the grid. So your range is going to go from -infinity to +infinity. So we've described our domain and range for this particular linear function. For this next graph, we have y equals -x minus 2 all squared plus 3. Once again, if you were asked to graph this by hand, you'd want to build your own table of values. If you weren't sure where to start on that table, what you could randomly start doing is selecting x values and seeing what happens as you solve for y. So I might suggest something like maybe -3 for an x value, -2, -1, 0, 1, 2, or 3. This is going to be a more sophisticated shape than our last linear function, so we'd like to get a better look at how the graph is behaving. So over in the far right margin, we'll have lots of scrap work here. So if we have x, which is equal to -3, then y will equal -3 minus 2 all squared plus 3. So if we clean up this work, we've got a negative outside the bracket. -3 minus 2 is -5. We'll still square that and add 3. And be careful here, you have to do the square part first. So -5 squared is a +25. +25 times the negative in front is going to be -25 plus 3. So in this case, -25 plus 3 is -22. Now that might be too extreme for us to graph, but it's good for us to have it in the table anyway. Next point, maybe x is -2. We'll see what happens here. So y is equal to negative, and then we've got -2 minus 2 in brackets all squared plus 3. So again, this is just a little bit of arithmetic. -2 minus 2 is -4, all squared plus 3. So y will equal -16 plus 3. Again, you have to square before you distribute that negative. -16 plus 3 is just -13. So we've got a second point that is a little more reasonable. Now, if x is -1, we'll have y equals negative, in brackets, -1 minus 2 all squared plus 3. So y will equal a negative of -3 all squared plus 3. -3 squared, or all squared, is +9, but 9 times -1 is -9. So we've got -9 plus 3, which we know is -6. So we're just filling in this table of values 1 point at a time. Now if x is 0, then we get y is equal to -0 minus 2 all squared plus 3. Inside those brackets, 0 minus 2 is negative 2 all squared plus 3. Essentially, when we simplify, negative 2 all squared is positive 4. 4 times negative 1 is negative 4 plus 3 is going to give us negative 1. Continue with this table of values. Quite a bit of scrap work here. If we have x, which is positive 1, or if we've chosen an x value of positive 1, then y will equal negative 1 minus 2 all squared plus 3. So you've got a negative out front. 1 minus 2 is negative 1 all squared plus 3. We get a y value of essentially negative 1 plus 3, or positive 2. 2 more to go here. If x is positive 2, then y will equal negative of 2 minus 2 squared plus 3. 2 minus 2 is 0. 0 squared is still 0. Times a negative 1 is still 0. 0 plus 3 is going to be positive 3. We've got one more point to go. If x is positive 3, then y will equal negative of 3 minus 2 all squared plus 3. So y will equal 3 minus 2 is 1. We'll have a negative 1 plus 3, or a positive 2. So we've got quite a few points to work with here. You might want to add to that table once you start building the graph, but what I'm probably going to do is avoid the top 2 points because those are far more extreme than the bottom half or bottom portion of this table of values. So let's build a grid and see what we come up with for an overall shape here. So we're going to draw in our x and y axes. Label those and make sure you have a proper scale. Here I'm counting, each tick is going to be 1. Or sorry, each line on your grid is going to be 1. So this will be 10. There we go. And then you're ready to start plotting these points. So the first ordered pair I actually want to graph is negative 1, negative 6. So when x is negative 1, I'm just going to switch colors here. My y value is negative 6. So there's our first point. Then we have 0, negative 1. So when x is 0, y is negative 1. We have the coordinate 1, 2. So when x is 1, y is 2. Then we have 2, 3. So when x is 2, y is 3. Then we've got 3, 2 again. So when x is 3, y is 2. Now, if I were to start picking more points further to the right, and I might want to do that, I might want to say, what's happening when x is 4? So if we do that, I'll just sneak this in as scrap work at the bottom. If x is positive 4, we'll have negative in brackets 4 minus 2 all squared plus 3. 4 minus 2 is 2. 2 squared is 4. So this becomes negative 4 plus 3, or negative 1. So that's going to give us a value of negative 1 when x is 4. So again, when x is 4, y is negative 1. What we're starting to see, I hope, is that there's some symmetry happening here. So if you choose x equals 5, you'll see that even more. So if we connect the dots and can kind of imagine that this is a parabola or parabolic shape. Oops, let's fix that tail here. Smooth curve on both sides. Again, your sketch is probably much nicer than this one. It's a little bit tough to do freehand sketches on these whiteboards. But essentially, you're going to have sort of that upside down U shape. This is called a parabola. Now, the last thing we want to do on top of graphing is to determine, once again, the domain and the range. So the domain of the function is left to right. So we're saying how far left does this graph go to how far right does the graph go. So the left tail sneaks over further and further to the left forever. So we know the domain starts at negative infinity. The right tail of this graph sneaks over to the right forever, so we know that that's positive infinity. So domain is negative to positive infinity. Those are the x's. So again, how far left to how far right. When we talk about the range of this function, we're going lowest to highest. So the lowest y value is going to be negative infinity because these tails are heading towards the floor, right? They continue forever. The highest y value is going to be right at the vertex here, and we know that the y value at the vertex reaches a maximum of positive 3. So my range is going to go from negative infinity to positive 3, and we have to use a square bracket at 3 to include that value because we know the graph touches that as its high point. So the range of this function is negative infinity to positive 3. So our last function, or our last relation, we'll see what it is in just a moment, is going to be x plus y squared equals 3. So if we want to solve for y, sometimes that's easiest for two reasons. One, it helps us to determine what our x values are and then figure out what the y values are that correspond so we can pick our input and get our output. Aside from that, if we wanted you to graph this on your calculator, you'd have to solve for y anyway. So let's just solve for y and see what happens here. If I get y by itself, I first want to start by taking y squared and subtracting x from both sides. So that's going to be 3 minus x. Now, if we want to get rid of a square, the opposite of squaring is square rooting. But remember, when you square root something yourself, it has to be plus or minus. So if I square root both sides, I'll get y equals plus or minus the square root of 3 minus x. So from here, it becomes my chore or my job to fill in a table of values. So if you don't have a calculator, or if you're not allowed to use a calculator, finding a good number for x when you involve roots like this might be a little bit challenging. So you may have a few extra values on your table that you don't actually graph. So one of the things I want you to be mindful of, though, is the fact that this is the square root. And we know we can't take the square root of a negative number, but it doesn't mean that we're not allowed to choose a negative value for x. So here's an example of what I mean. If we choose x equals negative 1 as an example, over in the margin, we're going to say if x is negative 1, let's see what happens with y. We'll have y equals plus or minus the square root of 3 minus a negative 1. And we know when you subtract a negative, it becomes positive. So 3 plus 1 is going to be 4. Now the square root of 4 is just 2. So we can simplify this as y equals plus or minus 2. So what's happening here right away is we can see that for every x value, we're going to have potentially 2 y values. What that means is this is not a function. This is a relation instead, because if it were a function, every x only has 1 y value that is mapped to it. So from here, we want to pick a few more values so that we can get a good feel for what this graph is doing. If you picked negative 2, let's say, so I'm going to sneak negative 2 in. Watch what happens here. If x is negative 2, then you get y equals plus or minus the square root of 3 minus a negative 2, which is really 5. Now, the square root of 5 is not a nice number. It's an irrational number. So chances are pretty good if I didn't have my calculator, I wouldn't want to use the square root of 5. So let's pick some other values and see if we can't come up with something that's a little bit better. If I choose x equals 3, that's strategic as well. So if x equals 3, let's show you why. You've got y equals plus or minus the square root of 3 minus 3. 3 minus 3 is going to be 0. So really, we say what's plus or minus the square root of 0? Well, really, that's just 0. So 3, 0 is going to be another point on our graph. Now, aside from that, I can't actually pick any values that are higher than 3. Let me show you why. If I choose x equals 4, as an example, we'll have y equals plus or minus the square root of 3 minus 4. But all of a sudden, that means we're trying to take the square root of -1, and we know that's imaginary. It's not something that can be graphed. So we can't pick any values of x that are bigger than 3. We need to head back towards the negatives. So you might want to choose a value, let's say, of x equals -6. And I know my table's out of order now, but that's okay. We're just building a table kind of hands-on here. So if x is -6, then we get y equals plus or minus the square root of 3 minus a -6, which is really 3 plus 6, or 9. So this is going to be plus or minus the square root of 9, which we know can be simplified as plus or minus 3. So once again, the same x value maps to two different y values. So I've just got a handful of points here. Again, you can choose more points on this table, but I want to show you how this is starting to line itself up. So if we draw your grid or your axes, again, make sure you include proper labels when you're graphing or when you're asked to graph. And we're counting, in this case, every tick is going to be worth 2, but every line on your grid is worth 1. So 2, 4, 6, 8, this gives us positive 10 here. And positive 8 for the y's on the top side. And then we've got negative 10 and negative 8. So the first point on the grid that was a nice point for us to graph is going to be -1, and when x is -1, y has two values. So when x is -1, y is either positive 2 or it's -2. So we have 2 points in the same vertical line. Automatically, we know this fails the vertical line test, so this is a relation and not a function. The next point we have graphed is 3, 0, so when x is 3, y is 0. And then the last one we chose is -6 and plus or minus 3. So when x is -6, y is positive 3, or y is -3. So if we picked a few more points further along the way, we would see that this kind of looks like a U-shaped graph or a parabola, but it's sideways this time. So I'm going to do my best to connect the dots here in a way that looks nice and smooth. Oops, missed that one. Let's try that again. There we go. And what we see here is that this is definitely a relation and not a function. But furthermore, let's discuss the domain and the range. So the domain of this function is left to right. Now these two tails are heading towards the left forever. So the domain is going to start at -infinity, but it's going to stop as far right as this graph goes, which is right along that intercept. So the domain in this function is going to go from -infinity to +3 with a square or inclusive bracket, because that's as far right as this graph is going to go. Range is bottom to top or low to high. Now this tail at the very bottom part of the graph is sneaking downwards forever, so I know that my range is going to start at -infinity. This tail of the graph is sort of sneaking upwards forever, so I know the top side of my range is going to stop at +infinity. So once again, we've been able to sketch these graphs by hand and figure out what our domain and range are. The last parts of 9.2 are showing us how to recognize functions and recognize things that are written so that they are not functions. So if you have a function, you know it's a function if it's written in function notation. So if you see something like f of x is equal to x squared plus 5 as an example, because we've used function notation, we know it's a function. So that's nice and easy, but what if things are not functions? This is where we've got to be careful and mindful of what our graphs look like. So the criteria I want you to look at for something not being a function are one of two things. If you see an equation with an absolute value symbol, so those straight lines up and down, and a y inside, we know that this is not a function. So here's the reason that that is. If I have x equals the absolute value of y, let's say x is 5. I could say if x is 5, then my y value is 5 as well, because if we take the absolute value of 5, we still get 5. Or we can say if x is 5, truth be told, y could also be negative 5, because remember, if you take the absolute value of negative 5, you still get 5 overall. So that's why the absolute value with a y inside tells us we have something that is not a function, because the same x value, so in this case x equals 5, corresponded to two different y's. Y was either positive 5 or y was negative 5. So absolute value symbols with a y inside mean you have things that are not functions or considered relations. Next, we have y to an even power. So by even power, we mean y squared or y to the 4th power, or let's say y to the 6th power. And a very quick and easy reason for that is if we said, let's say you've got y squared is equal to x. So if x were, actually let's work it from the other side. If I have 4 and I square 4, 4 squared would be 16. But guess what? So is negative 4 squared. That gives me 16 as well. So if you consider that the right side of the equation is my x value, and the left side in that brackets is the y value, my x value of 16 corresponds to two different y values. It could be positive 4 or it could be negative 4. So once again, the same x maps to two different y's. So if you see y to an even power or the absolute value of y, you are going to have a relation instead of a function. So we can use those two criteria to talk about whether or not the following equations listed in example 4 are in fact relations or functions. So if we have y equals x squared plus 2 times x, I don't see an absolute value with y inside, and I don't see a y raised to an even power. So that tells me automatically we have a function and not a relation. In part B, we have y equals the absolute value of x plus 4. And again, we want to be mindful that in this case, it's an x inside the absolute value symbols, not a y. So once again, this is telling us we have a function. By the way, if we were to graph the first shape, it would be a parabola or a U-shaped graph. We'll get into these functions a little bit later, but an absolute value function, or part B, is actually a V-shaped graph. So we've got a V-shaped graph in part B. But again, we'll entertain some of those questions a little bit later. In part C, we have x squared plus y is equal to 5. Again, we're looking for the absolute value of y, or y to an even power. None of those criteria are occurring in this example, so we know once again this is a function. In part D, all of a sudden we have y to an even power, or y squared. So if you have y squared minus x squared is equal to 6, that y squared, that piece of the equation in this case, is telling us that this is a relation or not a function. Last example we have here, part E, x plus absolute value of y is equal to 6. Again, that absolute value of y is one of the two criteria that tell us we have a relation instead of a function. So we know for sure this is also a relation. All right, folks, lots of ground we covered in 9.2, so please make sure you have a look at the homework questions. And as always, if there are elements in those practice questions that are causing you grief or causing a little bit of confusion, please make sure you reach out and let us know.